Alright, let me show you a nice resource here. We have this linked in the notes. I can find it on the resources tab. I'm starting to actually put stuff on there now. Let's see. Yeah, this first link is a good reference for, just duplicated that page, for system calls. We're probably mostly just going to use sysread and syswrite, sysexit, but we might use the sysopen and close to do some file opening and closing. Not too likely to use any of the others. There are, of course, quite a few of them, as you can see here from the number of pages available. But if we just take a look at sysread and syswrite, what this actually does is bump us over to what looks a lot like something that defines a C function, and it actually is defined that way. But this basically lets you look at the individual parameters and get a description of what they mean, as well as what the return value is. What we're going to see when we run these is that we put the code for the system call into EAX. So for a sysread, that would be a 3. For syswrite, that would be a 4. For sysexit, for example, that would be a 1. Then in some of the other registers is where we put some of the other parameters to the system call. And that's where it's a little bit different than what actually happens with library functions, which when we learn about library functions and how to call functions and what's referred to as the function call conventions, and we learn about the stack, we'll see that it's quite different. But for system calls using the interrupt mechanism, we need to put the parameters into registers that system call is going to need. That's in part, that means that you cannot use those registers for something else when you're using them for this. So that brings to mind once again that registers are generally temporary variables, and anything you want to be a little bit more permanent, you need to swap out to some location in memory, so that the registers can be reused for other purposes. But at any rate, so here we see what the sysread needs. It needs an unsigned int fd, fd for file descriptor. We'll see what that means in a moment. We need a pointer to a buffer. So it's basically a character pointer. Don't worry about this underscore user keyword. The main issue is it is a character pointer. That's what we care about. And a size t count. Well, a size t count is basically an unsigned integer. There are contexts where it might be an unsigned short integer and so forth. So that's why it's size t and not simply one of those more familiar data integer types from C. But at any rate, we need those things in the EBX, ECX, and EDX register respectively. So this pretty much tells us what we need to do in order to use a sysread, except you may not know what a file descriptor is. Here, a file descriptor is simply an integer that is telling us what file to read. And that file, in the case of getting input from the user that the user types in, is going to be the standard input file, and that is simply here a... Actually, let me double check, because I often goof those up. Let's see. Yeah, standard in is a 0. Okay, so we want a 0 here for the file descriptor. So we want a 3 as the sysread code itself. We want a 0 as the standard in file descriptor. We want the address of the buffer where we want the individual bytes stored, and we want the size of that buffer. One thing we don't want it doing is to try to read more bytes than the buffer size and to try to store those bytes in areas of memory that are not part of the buffer. That could lead to bad things happening in your program. I'm sure you recall from C programming that you want to be very careful that you don't get array indexes out of bounds. Well, setting a maximum size for your buffer is a way to prevent the sysread from going out of bounds of your buffer. Alright, so that's all the pieces of information that we need. So if you need to remind yourself this, or if you want to experiment at some point, you end up experimenting with other system calls in your assembly language programs, this is one place to go to pretty much get the details on all of them. And again, if you click the command, it's the system call itself, you can get a fairly detailed description of what it does, what its return value is, and so forth. And the other thing I will say is that when we do these system calls, the return value is going to be stored in register EAX. So we put the code for the system call, but what comes back will be its return value. Now we can see here that, again, it's returning, here it's an S size T, but still basically it's an integer, okay? I believe the first S is signed. That way it can return error messages, negative values if there's some kind of error. So we can read without error, we can read 0 or more bytes. If some kind of error happens when it attempts to read, we'll get a -1 back. That would be perhaps we attempted to read past the end of file. That would be one situation where you could get an error. And we could actually use this then to read until end of file. Well, it would be, technically we'd be reading until there was some error in our attempt to read. But the most common thing would be the attempt to read past the end of file. So that's the sysread. And now let's see how we use that in assembly language. If I can bring up our virtual machine again. There it is. All right, so we need to set that up. So if we recall, we want to put the code 3 into EAX. So EAX and OXO3. Now you could just use decimal 3 there, but I like to get in the habit of using hexadecimal in a lot of different places in assembly language programming, and it's a good habit to get into. You should just become familiar and become comfortable with hexadecimal. So why not? Now, I like to put the code last. I like to put these in reverse order. So I'm going to move into EDX, move into ECX, whatever, and move into EBX, whatever. Now, EBX, this is the file descriptor, and that is 0 for standard input. So let's put OXOO there. Three is the code for sysread. That's why we're putting a 3 there. And now we still have to put the other two parameters in here. ECX, let's double check what that is. So ECX was the address of the buffer. So what we're going to want here is our in-buffer address from right there. And I like to keep my comments lined up, so I'm going to slide these over. All right, so that's the address of the buffer. That needs to go into ECX. And finally, EDX was the size of that. We could put the 80. We could put OX50 because that's 80 in hexadecimal. Or let's use our buffer size symbol that we've already defined. So, and that's the size in bytes. And that simply prevents the sysread from trying to read too many bytes and overflowing the buffer. Something we do not want to happen. And finally, we use the int instruction with the code 80. So we're doing an interrupt code. Well, that's not an 80, that's actually a 128. Which is a system call interrupt. So once this basically our program is going to interrupt itself to generate the system call. It'll have the necessary data in these registers for that system call to do its job. The system call will do its job. It'll go and attempt to read standard input, and it'll only read up to one line. So just to describe what the sysread does. It'll read up to buffer size bytes or until it hits a new line character, whichever comes first. And since we'll be able to do this in the debugger, we'll be able to see exactly what goes on there. Now, in fact, I am going to bump this down to something small like 10, just so we can play around with too much input more easily. We'll bump that up to 80, and then we'll probably bump it up to 1,000 when we're done. But let's go ahead and set that at 10. Now, so this reads a line, and now let's just print the line back out. This is not our ultimate goal. This is just to make sure we understand how the system calls work first. Then we'll go on to a little bit more interesting example. So let's do move into EDX. Well, this is an interesting question. What do we move into EDX? We don't want the entire buffer. Let me go back to thinking about a buffer size of 80 here for a moment. We don't want to put buffer size here. And the reason we don't is we may not have read in 80 characters. What if the line only had 10 characters in it, 10 bytes? If the line only had 10 bytes, then we only want to print 10 bytes back out, right? So how do we find out how many bytes was in the line? Well, remember, I actually already told you to answer that. Can you pause and see if you can figure it out before I tell you? All right, if you pause and figured it out, great. But now I'm going to tell you, let's come back over here and look at that sysread again. The return value. On success, the number of bytes read is returned. Okay? And all system calls are going to put that integer return value into EAX. So EAX, after the sysread, EAX will store. So I'm just going to put that here as a comment. After the sysread, the return value, number of bytes read, will be in EAX. All right. So instead of moving buffer size to EDX, I'm going to move EAX. Copy the number of bytes read, return value of the sysread, into EDX. Now I'm going to add a comment here. This will only work if the read is the last thing we did. So if I put other stuff in here that changes EAX, this ain't gonna work, right? That's not gonna work at all. So we have to be careful. Immediately after the sysread, EAX will have that number we want. Later on, we're gonna want to do some stuff in between here, so we may want to make sure that we save this number. But for now, it's gonna work just fine. And then moving on, what do we need in ECX? Well, ECX is going to be the buffer, and that's still going to just be the in buffer because we're just printing out the line we read in. Then we have EBX, and here we need the file descriptor of OXO1. That's standard out. So the file descriptor 1 is for standard out, standard output. And normally, standard output means output to the terminal that the program is running in. So now let's finally put into EAX the code, and that should be a 4 for SysWrite. And then we want to do, so again, we do a system call interrupt. So int makes it an interrupt, and the 128 that we put here makes it a system call interrupt. All right, and finally, let's just go to one of our other programs and get our yeah, these are our 3 instructions that do the exit. Let's bring that over. So these are our exit system calls, and I'm just going to label this, even though we don't really need this label. It's kind of nice to know, just to kind of label it and remind ourselves what's going on here. And just to, for the sake of completeness, let's go ahead and look at the documentation for the exit system call. If I can bring that up again. So here we are, and we can check the system exit. So the code for that is a 1, and what we put, all it needs is in EBX, it needs an error code, and that error code will basically be the return code for the program. If you're familiar with Linux, all programs are expected to provide a return code with a 0 indicating the program had no problems, and any other number possibly indicating some kind of error. That's what it's asking for here. So sysexit will exit your program. It'll pass this error code back to the calling process. So that would be the shell process running in the terminal. So that's what we're setting up now. And for this, we're not really doing any kind of error code. We're just assuming that everything worked just fine. So we're giving it a return code of 0. And then the 1 is the code for the sysexit. And the only parameter of sysexit is the return code for the program. And once again, we do a system call interrupt. Yeah, so this is not, we're not doing all of this yet. We're not reversing the line, so we're not even using our output buffer yet. But we will be using that momentarily. But just to show that we can read something in and print it back out, just to do that much, let's get this working. So let's build and run this. So we do that, and we come back over here, and we want a nasm command -f elf32, and for now I'm not going to do it. Well, let's go ahead and add the debugging info, but first I'm just going to run it on the command line. But you can, even if you put debugging information in there, you can still run a program easily enough. So let's do that, and now what did I call this? Read and reverse.asm. So there we go. Good, no errors. So now let's do the linker. So linker elf I386 and read and reverse.o, and then -o, read and reverse with no dot anything. That'll be the name of our executable. And just to see what we've got here, that's what we edited in gedit. This is the backup file from gedit. This was created by the nasm command, and this is our final executable created by the linker. And you can see from the timestamps, the order in which they were created makes sense. All right, so now let's run it. So /read and reverse, and there it goes. It's doing a sysread. This is a little bit like a scanf that you're familiar with, or other input commands that you might be used to from C programming. But it's got some important differences. But okay, so let's do I don't know, A, B, C, D, E, F, G, and boom, it printed that line right back at me. So everything worked. Now let's go back to our program in the editor here. Let's bop that down. Bop the buffer size down to 10 so that we're only reserving 10 bytes here and 10 bytes here. And we'll be using 10 here and so forth. And let's just do a quick save. We'll rebuild and rerun, but this time we'll run it in the debugger. Once again, just a reminder, you should be doing this too, getting screenshots, following along, etc., etc. So pause as necessary to just catch up and get and do the same things and get screenshots. And let's see, nope. So we've rebuilt, and now I'm going to do kdebug, read and reverse. So there's kdebug, there's read and reverse there. Let's set a breakpoint on the first instruction, and we should be able to watch the registers here, the memory over here. I'm mainly interested in the input buffer, so let's put ampersand in buffer here. Oh, it's not going to show me anything. If you don't see anything, if you've not noticed this yet, you don't see anything over in these windows until you're actually running the program. So I've got the breakpoint set. Let's run it and have it pause. Okay, and here's what I've told you about before, where this green arrow comes out wrong. Now I did have somebody say they installed a more recent version of kdebug than what I have installed, and they claim that they're not getting this problem. I'm not sure. Maybe it just depends on what you put in for your program. But as you can see here, it did not stop on the first instruction. The first instruction is really right here. It's pointing to the second instruction. Now if we go over here and we do _start, and then we do the instructions view, it actually even looks like it thinks it's on the second instruction here, which may be that the breakpoint itself got misinterpreted. So we may actually have done that instruction. Let's see if we have buffer size in EDX. That'll tell us if we've really done this instruction. EDX does have a 10 in it, so we really have done that instruction. So it is pointing to the correct instruction here, but since I put the breakpoint on start, it should have stopped here when I clicked run. So it should have stopped before the first instruction, not after. So there is something a little bit funky going on here, so I'm probably going to go back and strip out my comments, because that seems to be what throws off the alignment of where it thinks the breakpoints are and so forth. One thing I can do right now is I can take that breakpoint out. If I go to the breakpoints here and I just put _start like that, that should work it. I'm going to hit run to make it finish the program. It's just going to do all the remaining instructions. Oh, well, one of those instructions is a sysread, so now our terminal is important. This terminal is waiting for me to input stuff, so let's do A, B, C, D, E, F, and get A, B, C, D, E, F back. Now the program finished. Okay, so now let's bring, actually, let's have the terminal side by side here. Okay, so this was just a different way to add that breakpoint expressly on the start symbol. So even though it kind of got confused about where the start symbol was here by my hitting the breakpoint here, it seems to know where it is. So let's go ahead and click run again and see if it finds. See, now it's definitely paused on the first instruction here, but over here it doesn't have the green arrow showing. So it's still a little confused. So that's why I strip out extra comments and so forth when we do this stuff. Okay, but we can work with this for now. Let's go ahead and bring up in buffer here, and let's just kind of do one step at a time. Look at what's going on in the registers. So I do a step over. No, it's definitely not making sense. Well, wait. Okay, I just put in EDX. Oh, I should be putting a 10 there, and it didn't do it. In fact, it's not coming back. Seems to be having trouble. It might be waiting for input, but it shouldn't have been on that instruction yet. Oh, wait. No, it's still confused about this darn breakpoint. It didn't find the breakpoint. That's what happened. I hit run, it didn't hit a breakpoint, but now it thinks it's stopped there, but it's not really running. So you can see KDBG definitely gets confused about the location of breakpoints or where this arrow should be pointing, because right now the program's not running. If you were wondering, this little heartbeat symbol will be animated if it has your program running. It's not animated. The program's not running right now, but it's showing us an arrow saying the program is running and paused on this instruction, which it definitely is not. So KDBug is confused. Let's exit KDBug. And let's go back to our editor and make a stripped version of our read and reverse program. So I want to keep the version with the comments just because they're instructional. So I'm just going to do a save as, and now let's do read and reverse. Trimmed. We'll call it trimmed. Yeah. Read and reverse trimmed. And now let's take out any extra lines of comments. And in fact, I'm going to define this constant at the bottom. I'm not sure if that's going to cause a problem having it up the top, but we might as well define it down here as well. and get rid of blank lines, any extra comment lines, there we go. Now it has no extra blank lines or extra comment lines in there. And that generally allows the debugger to keep track of where breakpoints really are and what line, what source code line to point to. So let's do that. All right, so let's click save. Now, again, if the student out there that said they tried Kdebug with a later version really was not, if it's really not giving you that kind of problem with exactly this file with all those extra comments and stuff in there, email me again about that, because I want to hear about that. Maybe I'll update. Unfortunately, that's not like in the standard repository, so it's a little bit of an extra step to get the latest version. At any rate, let's now save this. Go over here. We have to rebuild. So you turn a few times and come up here. We want to rebuild. Now we want to do it with it stripped. And I mistyped it. Oh no, I called it trimmed. There we go. And now let's do the LD command. Trimmed.o. Trimmed. And take off the dot. That's our executable. And there's our linker command. And finally, our kdgb command with the trimmed version. All right, now when we set our breakpoints and so forth, it should figure them out correctly. We can at least hope. All right, 8080, that sounds like the correct address for start, so I think we're already doing pretty well. All right, so let's click run. And now it's pointing correctly to the first instruction. Green arrow is at the right place. Everything's looking good. Let's put in ampersand in buffer here again so that we can see what's going on there. Let's do a bytes view. Hexadecimal bytes is probably fine, but well, let's do character bytes. Let's bring up the terminal window. As this down here, this is the where the terminal window shows up on your icon, in case you didn't notice what that looks like, and on your taskbar, I mean. And let's slide things around so we have the Kdebug window and the terminal window there together. I do have another Kdebug running from our previous example. I think I might as well shut that down, just so I don't have extra ones confusing things. All right, so we're ready to start doing the instructions. Let's look at registers here and memory there, and let's do a step. So we put the buffer size into EDX, a step, and we put the address of the buffer into ECX. We might want to look at that as a hexadecimal number. Might as well look at everything as hexadecimal numbers, because why not? So we have the 10 in EDX, we have the address of in buffer 80490B8, 80490B8, that's the address there in ECX that the syswrite, the sysread is going to need to know where to store the bytes it reads. And then we need to put the code for standard in into EBX. It already has a 0 in it, but we need to make sure that it has a 0 in it, so we do another step, put a 0 into EBX. Finally, we put the syswrite code into EAX, so EAX now has the 3, which is going to tell the interrupt to do a sysread. And now when we step over the interrupt, a whole bunch of machine language instructions are going to go off, because that interrupt is going to jump to kernel code, it's going to do its thing, and then come back. And we're not going to see those as individual steps. So we just do the step, and because it's doing a sysread, it's actually waiting for some input here. So let's give it some input. Let's give it A, B, C, D, E, F, G. All right, and let me slide these over so we can see everything. And sure enough, we see the A, B, C, D, E, F, G, and look at that, A/N. That's your new line character. So I want you to keep that in mind when you are working with sysread. It is going to pick up that new line character. One thing it will not do for you is put in a null terminator to make this a string, okay? You have to keep track of how many characters it read in, and if you want a string, you would have to put in the null terminator yourself. Here we happen to have zeros already, but I'll show you how that null terminator might trip you up later on. But for now, we're ready to print that same data out. So we put into EAX, or we put into EDX the number that came back in EAX. Let's look at that number. What's in EAX right now? Remember, we had a 3 in there. Now it's an 8. Okay? Hexadecimal 8 and decimal 8 look very similar. That's convenient. How many numbers did we type in? Or how many letters? I typed A, B, C, D, E, F, G, 7 letters, and I pressed enter. So that's 7 regular characters and the enter character, the new line character. So we read in exactly 8 characters. We did not fill the buffer, so that's good. And so now we want to print out that same buffer, so we're going to put an 8 into EDX for the syswrite, because syswrite needs to know how many characters to print. Then we will put the pointer to the input buffer, because right now we're just using the same buffer for both. And then we put the 1 for standard out, so that says print that output to the terminal. We use the code 4 for the syswrite, then we do the interrupt. So let's do step, 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 and finally do the system call. Those characters get printed out, and now the next few steps are going to do the exit system call, and we can just click run to finish those out, and the program is done running. And so that's the basics of how to use sysread and syswrite. So let's do one other experiment. So let's edit our program. There we go. I'm going to put the buffer size at 20 this time. Gives me a little bit more, not 200, 20. Oh, we're getting laggy input for some reason. Might have too many things running on my computer right now. Yeah, but I want to finish out this video, so we might just have to live with it. Okay, so here we did a read. I'm going to do a second read. I'm just going to copy and paste all this code. You know what? Maybe a better file name for this would be read-write experiments, and then later we'll do the read reverse. So yeah, let's do that. So we're going to do 2 sysreads in a row, and I'm doing this on purpose to show you something in KDebug after we build and run this. So let's just save that. We're doing 2 sysreads right in a row. And so let's come over here and run the nasm command and run the ld command and run the kdbg command, actually, and this is where, generally speaking, I recommend exiting kdbg when you modify the program. And then running it again, as I'm doing here. There we go. And so it's fired back up. I would take that breakpoint out, put it back in again, because once the source code's changed with extra lines, things might be moved around. The debugger might get confused about where that breakpoint really is. So let's do that, and now let's run it. And I'm just going to put another breakpoint at the beginning of the next read, and then at the beginning of the write. So now all I have to do is click run instead of doing everything step by step by step. And I'm also going to shrink my window here a little bit so I can bring the terminal window in, have it side by side. Whoops, I don't want it maximized. There we go. Bring this xterm window over here. Okay, so let's go ahead and hit run, and it's doing the first sysread. So let's go ahead and put some stuff in there. Now I made my buffer 20 long, so let's go A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. That's not the full 20. Actually, let's keep going. Q, R, S, T, U, V, W, X, Y, Z. This will illustrate a few things, actually. So let me fire that off. Now let's see what happened. We read in A, B, C, D, all the way up to T. That's 20 letters. 8 plus 8 plus 4 is 20. Yeah. So notice that it only read in the first 20 characters I typed. So that leaves U, V, W, X, Y, Z out there. So you may wonder what happens to those. Well, those will actually still be buffered for the next time we do a sysread. So when I do this sysread, it's going to pull in the U, V, W, X, Y, Z. Where is it going to put them? It's going to put them right back here in the same buffer. So it's going to should overwrite the A, B, C, D, E, F, G. So let's go ahead and click run. And so now it did that sysread. And notice it did not wait for me to type anything. Okay? Why did it not wait? Because it found it had some stuff to read, and there was a new line character in there waiting. So notice now that we have here U, V, W, X, Y, Z, new line character, but the other stuff in that buffer is still there. H, I, J, K, L, M, N, O, P, Q, R, S, T, that stuff is still all there. The important thing is look at this byte right here where my mouse is pointing right now. Notice, this is somewhat important. Notice that there is not a 0 there. There's a 72, a capital H. Not a 0, not a null terminator. The sysread does not do strings. It just does bytes of data, and it does not care what those bytes of data are. It doesn't do anything special with a 0 byte to indicate the end of a string. That is something that, if you wanted that, your program would have to do. Okay? And that, for example, is a difference between, say, using a scanf or some of the other C library functions to read strings. They will put a null terminator at the end of your string. Now, if you don't know what I'm talking about, a null terminator, maybe just Google that, okay? I'm not going to try to explain it right now, but hopefully in your 250, if not your 150 class, null terminators were discussed. They should have been discussed. So Google C programming strings null terminator, okay? You might pause and just Google that now and take 5 minutes to learn about null terminators a little bit, just so you understand what I was talking about. Now, we've overwritten part of that buffer, And now we're about to go on to do the syswrite. So how much are we going to write? Well, we're going to move into EDX whatever's currently in EAX. What's currently in EAX is the 7 from the second syswrite. Okay? So this first write read 20 bytes, and that was in EAX before, but doesn't matter now. It read 7 the last time. That's what's in EAX right now. That's what we're going to put into EDX. So that's what we're going to tell syswrite to print. I'm sorry, I think I said syswrite earlier when I meant sysread. So we did a sysread of 20 bytes. That's what came back into the EAX register. Then we did a sysread of 7 bytes. So 6 letters followed by a new line. 7 bytes were read in, so that's what's in there now. That's what we're putting in EDX. So we're going to write those 7 bytes, not any of the other bytes. So let's go ahead and click Run to do the syswrite. So we went through all those instructions from there to there, and sure enough, all we print out were those 6 bytes. And notice where the cursor is in the terminal window. It's on the next line. That means it also printed out the new line character that we have right here. So it printed all 7 of these bytes, including the new line character. And so the cursor is dropped to the next line. Now, let's go ahead and finish out the program. Let's run it again. I want to show you one other thing here. So we're running, and now I'm not going to put more characters than can fit, so I'm going to hit Run to do the first sysread. So let's come over here, and now let's do just to be different, 1 2 3 4 5 6 7 8 9 10 exclamation point @ pound dollar percent caret ampersand. That should be enough. That's not 20, so I think we're good. All right, now we see the characters 1 2 3 4 and so forth. And then the character exclamation point @ pound sign, dollar sign, and so forth. All in there. Great. We did not read 20 characters. We read, looks like we read 18 characters. Okay. So far, so good. And we're ready to do the next sysread. Now, because we've read everything that was out there, including the /n, including the new line character, the next sysread is also going to pause and wait. So I'm going to click Run, and notice the arrow over here did not move because it's still doing the sysread. It's actually on this instruction right here, but apparently it doesn't want to jump it down there. It's just going to sit there until it finishes execution, then jump it all the way down to here. So the sysread is going, and it's waiting for me to type something. So now I'm going to type, I don't know, quirt. All right. Whoops. I need to click in that window first. Quirt. There we go. And hit return. And so again, we see partially overwritten QWERT and the new line character all went in there. Okay. And filled in that buffer. Looks like I accidentally clicked on something to make another breakpoint there. I don't want that. And so now it's ready to do the syswrite. Once again, it's going to copy the 6 from EAX into EDX and use that as the number of bytes for the syswrite to write. So let's click Run and just see that happen. And so all we see coming back is quirt, and hopefully this clarifies what syswrite and sysread actually do. So far so good. Let's let that finish out. Let's exit KDBG, come back to our program, and so finally what we're going to do is modify this to read and reverse the input lines, and we'll put that all in a loop so it can do multiple lines. Okay, but actually let me see what I'm doing on time here, because this has been pretty good so far. We're actually bumping up on 50 minutes, so I'm actually going to end this video here. We're going to pick up with the next video right where this one left off, and actually finish the example program that I promised we were creating from the start, which is something that will read lines of text, print them in reverse, and just keep doing that over and over and over again. So that's going to need, it's actually going to need a loop within a loop. One loop for reading the lines, and another loop inside that loop to reverse and print the lines. So we've got a fair bit of stuff to add to this program, and we're actually going to delete some of what we have in there. But that's what we'll pick up on the next video. So maybe this won't be the last week 5 video, because I do want to finish out this example before we are for this week, because I want you to be able to use it to do the first assignment. All right, so anyway, but signing out on this video.